Hello everyone and welcome to today's class. It is our first lesson on the topic turning effect of a force. So as always, let me start by giving you the quote of the day, which states that if you don't take time to heal from the pain of your past, then be prepared to bleed all over your future. So we'll discuss that quote at the end of our class today. So today we are discussing about the turning effect of a force, which is our third topic in the Form 2 work. So first of all, we need to understand the terms that are constituting or making up our title. So turning is just from the word to turn. To turn maybe is to change the direction of anything. Maybe if it was facing in the east direction, you make it face in the maybe west direction or even the northern direction, but it has to be as a result of a force. An effect is just the cause of something on a particular thing. Then a force, we did say that a force is just a push or a pull of an object. A force is a push or a pull of an object. So we did look at various effects of force on an object. That is in a given topic in Form 1 work, which was actually called the force. So we did say that a force is measured in newtons. Then we said that the four effects of force on a body are: 1, a force can start motion of a stationary object. Then 2, that a force can actually stop motion of a moving object. Then 3 is that a force can change the shape of an object or it can distort an object. Then 4, that a force can change the direction of an object. So actually a force can bring about a turning effect. It can bring about a turning effect, which is very close related to changing the direction of an object. So remember, the object can be either moving or stationary. So because of that turning effect, that is because a force can change the direction of a moving object. Therefore, we are looking at how a turning effect is brought about by a force. So the turning effect of a force, that is what we call the moment of a force. So if you are asked to define what is moment of a force, you can alternatively say that the moment of a force simply refers to the turning effect of a force. So the turning effect of a force is called the moment of a force, or sometimes we just call it the moment. So it can be moment of a force or simply moment. So do not confuse moment with another term that we'll discuss in Form 3 called momentum. So for this case, we are looking at just the word moment or moment of a force. So mathematically or in physics, how do we define the term moment of a force? So moment of a force is defined as the product of the force applied and the perpendicular distance from the pivot to the line of action of force. So we are saying that moment of a force is defined as the product of the force applied and the perpendicular distance from the pivot to the line of action of the force. So if you look at that definition closely, we are talking of the word product. So product in mathematics actually means multiplication. So if you are saying that the moment of a force about a point is the product of the force applied and the perpendicular distance from the pivot to the line of action of the force. So we've said that product means multiplication. So it means mathematically moment of a force will be equal to the force, that is the force applied, times the perpendicular distance from the pivot to the line of action of that force. So we are saying that moment of a force is defined as the product of the force applied and the perpendicular distance from the pivot to the line of action of the force. Although if you also define moment of force as the turning effect of a force, you will still be given a mark. But a better definition, or mathematically that is a definition that will give us the formula for finding the moment of a force, is that moment of a force is the product of the force applied and the perpendicular distance from the pivot to the line of action of the force. So it is simply force times, because times represents the product, force times the perpendicular distance from the pivot to the line of action of the force. So in terms of symbols, force is always represented by capital F. Then perpendicular distance, in this case, we represent it by small d. So if you are saying that moment of a force is the product of the force applied and the perpendicular distance from the pivot to the line of action of the force, then it means mathematically moment of a force, or simply moment, will be given by force times d, that is the force applied times the perpendicular distance from the pivot to the line of action of the force. Now, if you are talking of the line of action of the force and the perpendicular distance from the pivot, what do this represent? So if you look at our diagram here, which is constituting of a lever, actually a pivot, or what we are calling the fulcrum, or the point of support, or the turning point, then if you measure the perpendicular distance, that is the turning point. This is actually where we have the turning point. Then we have a force acting downwards from this particular side here. So if this is our force, then actually the line along which actually our force acts from, this is representing the line of action of our force. So this is what we are calling the line of action of the force. Then the perpendicular distance, you measure the distance from the force, that is the line of action of the force, from the pivot. So the distance from the pivot to the line of action of the force, that is what we are calling the perpendicular distance, which we are representing by small d. So we are saying that actually moment is the force applied, the product of the force applied. This is our force applied, this is the force applied actually, is the product of the force applied and the perpendicular distance from the pivot. This is the perpendicular distance from the pivot to the line of action of the force. This is our line of action of the force. So you must be very careful where you are measuring this perpendicular distance. The perpendicular distance must be measured from the pivot, or what we are calling the fulcrum, or the point of support, or the turning point, to the line of action of the force. So it must be perpendicular. Perpendicular means it has to meet the line of force at an angle of 90. That is the angle from here up to actually our bar here is 90 degrees. It must be 90 degrees for us to say it is perpendicular, or sometimes we use the word normal. So in short, we have just said that moment of a force is the product of force applied and the perpendicular distance from the pivot to the line of action of the force. Then mathematically we are representing it by force times, because this is what represents the product, times the perpendicular distance, or simply Fd. So moment is given by Fd, that is force times the perpendicular distance from the pivot to the line of action of a force. Then in real life examples, what are the examples of activities in which a force produces a turning effect? Remember, the turning effect is what we are calling the moment. So what are the examples of activities in real life situation where actually a force produces a turning effect, or what are the activities in real life situation whereby moment is applied? So the first activity where a moment of a force is actually applied is that one, it is easier to open or close a door with the handle far from the hinges. So it is easier to open a door, open or close a door with the handle, that is the place where you hold while you are closing or opening the door, far from the hinges. So remember, the hinges in this case are the turning points. That is actually where the door turns, either as it closes or it's open. So the hinges in that case represent the pivot, or what we are calling the fulcrum, or the point of support, or the turning point. Then the handle represents the region actually where the force is applied. Then the distance from the hinge to the handle represents the perpendicular distance, that is from the hinge, which is the pivot, to the line of action of the force, that is the handle. So that is one case where actually moment of a force is applied. So the first application of moment of force is that it is easier to open or close a door with the handle far from the hinges. So it is easier because the perpendicular distance is actually larger. That is when the handle is very far from the hinges. So it means in that case the pivot is far away from the line of action of the force. Therefore the perpendicular distance becomes larger. The second scenario where we apply the turning effect of a force or the momentum in real life situation is that one, the second effect is that, or the second application is that it is easier to tighten or loosen a nut or a bolt using a longer spanner than a shorter spanner. So remember, when the spanner is long, it means actually its handle is far from the actually the bolt. That is the bolt that is being either tightened or loosened. So when the bolt is far away from the handle, it means actually the perpendicular distance is larger. So when the perpendicular distance is larger, it means the moment produced will be larger, because it means you are talking of a larger perpendicular distance. So a force with a larger perpendicular distance from the pivot will actually produce a lot of moments, or will produce a lot of moment of a force. So actually the second application is that it is easier to tighten or loosen a nut or a bolt using a long spanner than a shorter spanner. Then the third application of moment of a force is that it is applied in riding or cycling, riding a bicycle, or even cycling a bicycle, or even riding on a seesaw. So remember, a seesaw involves actually maybe two people or two bodies, one sitting on the right hand side, then the other one sitting on the left hand side, with a pivot or the turning point or the fulcrum at the center. Then these particular objects are actually balanced. Even the working of a beam balance, that is when they are measuring maybe the weight of meat. If you go to any butcher, most butchers actually do not have electronic. Some of them have the manual, what we call the beam balance. So the beam balance also applies the moment of a force. Why? Because one object is placed, maybe a mass of 1 kg is placed on one side, then a meat is also placed on the one side. So if they realize that the meat is balancing with 1 kilogram of that standard particular object, then it means actually the meat is also 1 kilogram. That is provided that the distance from the pivot to the line of action of the force, or the distance from the pivot to the object, that is the 1 kilogram object, and the distance from the pivot to the meat is exactly the same. So if they balance, then they will realize that that meat is actually 1 kilogram. So that is another application of the turning effect of a force. That is in riding on a seesaw. There are several applications. I can give you the fourth one. The fourth one is in steering the car. That is when a car, when you are steering a car, actually the force is applied on that steering car so that it can turn in the desired direction. Then another application, that is the fifth one, is that when you are closing or opening a tap, actually moment of a force is applied, because we have the perpendicular distance, we also have the turning point, and you also have the force or the line of action of the force. So those are just a few examples where turning effect of a force is actually applied. So one, you have said in opening or closing a door. Two is in loosening or tightening a bolt using a spanner. Three is riding a seesaw or even cycling a bicycle. Then four is in closing or opening a tap. Then the other application is in steering a car by applying some force on the steering wheel. We look at an example actually involving the formula that you have just talked. So you have an example here reading, find the moment of a force about Q in the diagram below. So if you are told to find the moment around Q, it means actually Q is our turning point or the pivot, or sometimes what we call the fulcrum. So we are required to find the moment of a force about point Q. So it means Q represents our turning point. So Q represents our fulcrum. So we've said that moment of a force is given by the product of the force applied times the perpendicular distance from the pivot to the line of action of the force. So if this is our pivot or the Q, then the force applied actually here is the 10 Newton. Then the perpendicular distance from the at our turning point to the line of action of the force, this is the perpendicular distance. In this case it is actually 30 centimeters. So the product of this force and the perpendicular distance from the pivot to the line of action of the force, that will give us the moment of our force about Q. So in this case, moment of a force will be given by the force applied times the perpendicular distance from the pivot to the line of action of the force. So the force applied in this part A is actually 10 Newton. So we'll take the 10 Newton multiplied by the perpendicular distance from the pivot, that is from Q up to F, is actually 30 centimeters. Then remember, because the moment of a force is given by force times perpendicular distance, it means the SI unit for the moment of a force will actually be Newton meter. Why? Because the unit for force is Newton, then the unit for actually distance is meter. So it means if you combine those two, we are looking at the product, or we are multiplying those two. So we are saying that the SI unit for moment of a force is actually Newton meter. It is Newton meter. So that means that for you to find the moment of a force, it has to be Newton meter. Therefore it means the force has to be Newton, then the distance has to be in meters. So because the distance here is in centimeters, we convert it into the SI unit for length, which is the meter. So we actually have 30 divided by 100, that is to convert it from centimeters to meter, because remember that 100 centimeters is equals to 1 meter. So if we convert 30 centimeters into meter, we divide by 100, so that the 1 0 and 1 0 cancel, so that we have 10 Newton times 0.3 meter. So 10 times 0.3, you will simply get 3 Newton meter. So these are the units for moment, or the moment of a force, Newton multiplied by meter, so the Newton meter. Then we also look at another case scenario here. We are also required to find the moment of a force about Q. So we said that moment of a force is given by the product of force and the perpendicular distance from the pivot to the line of action of the force. So our Q is here. So because it is about Q, it means Q is our turning point, or the fulcrum, or the pivot. So the perpendicular distance from the pivot to the line of action of the force, you realize that this line is not meeting with the line of force at 90. So this cannot be the perpendicular distance. So that means we formulate another line which would meet our line of action of force at 90, or perpendicular. So this will represent the perpendicular distance from the pivot, which is our Q, or the turning point, to the line of action of the force, to the line of action of the force. So because we are given this as 5 meter, then this is 3 meter, and this line is meeting the line of action of force at 90 degrees. It means this is actually a right angled triangle. So if it is a right angled triangle, that means we can apply what we call the Pythagoras theorem from mathematics. So Pythagoras theorem simply states that the square of the hypotenuse is equals to the square of the base squared plus the square of height. So if we make base the subject of the formula, it means base squared will be equal to hypotenuse squared minus height squared. So the base alone will be equal to the square root of hypotenuse squared minus the height squared. So the hypotenuse in this case, remember the hypotenuse represents the longer distance. So the longer distance from Q up to this particular point is actually 5 meters. So we'll take the 5 squared, which is our hypotenuse in this case, minus the base squared. The base is actually 3 meters minus base squared. So this 5 squared, you actually get 25. Then 3 squared, you get 9. So 25 minus 9, you actually get 16. So the square root of 16, you simply get 4 meter. So it means our base here, which is representing the perpendicular distance from the pivot, or the turning point, to the line of action of the force, is actually 4 meters. So that means the moment of force in this case about Q will be given by the force applied times the perpendicular distance from the pivot to the line of action of the force. So the force applied is simply 6 Newton. Then perpendicular distance. So you should never make a mistake. You must ensure it must be the perpendicular distance from the pivot to the line of action of the force. So if you took 5 meters as your D, or the perpendicular distance, it will actually be wrong. Why? Because this 5 meter is not the perpendicular distance. That is the 5 meter from Q is not meeting our line of action of force at an angle of 90. That is, this angle is not actually 90. It is likely to be more than 90 degrees. So your perpendicular distance must be the perpendicular distance from the pivot, strictly from the pivot to the line of action of force. They must meet at 90. It must be a perpendicular distance. So that's why we are not using 5 meter. Instead, we are using the 4 meters, because this is a line that meets the perpendicular distance, that meets the line of action of force at 90 degrees, and it is drawn from the turning point, or what we call the pivot. So we'll have moment of force times a perpendicular distance. So this will be, the force is 6 Newton. Perpendicular distance from the pivot to the line of action of the force, that is the line that meets with the line of action of force at 90, is actually this line and not this line. So this line, you have calculated this at the base, which is actually the 4 meter. So that will be 6 Newton times 4 meter, which gives you 24 Newton meter. So remember, we said that the units for moment of force is actually Newton meter. So this will be 24 Newton meter. Then we look at what we call the principle of moments. We look at what we call the principle of moments. So a principle is just a rule or a law that guides us on how actually moments should work. So the first question is, what does the principle of moments state? How does the principle of moments state? So if you are asked to state the principle of moments, you simply say that the principle of moments states that for a system in equilibrium, the sum of clockwise moments about a point must be equal to the sum of anticlockwise moments about the same point. I've said that the principle of moment of force states that for a system in equilibrium, the sum of clockwise moments about a point must be equal to the sum of anti-clockwise moments about the same point. Yeah? So when we talk of the clockwise moment, remember the principle of moment, sometimes we call it the law of levers. Sometimes the principle of moment is called the law of levers. So if you are asked to state the law of levers or to state the principle of moment, you simply say that the principle of moments or the law of levers states that for a system in equilibrium, the sum of clockwise moments about a point must be equal to the sum of anti-clockwise moments about the same point. Now, what do we mean by clockwise moments and what do we mean by anti-clockwise moments? So remember, the word clockwise moment, the word clockwise is coming from two words. That is the word a clock and the word wise. So when we say something is wise, for example, likewise, it means it is behaving in a similar manner. So when we are talking of a clock, you know that a clock usually moves. That is a wall clock. It moves in this direction. That is the minute hand clock and the hour clock actually moves in this direction. So this direction is what we are calling the clockwise direction. The clockwise direction. So forces that causes the bar, this bar of ours, to move in a direction that is similar to that of a clock or that is clockwise, then such forces produce a moment called the clockwise moments. So we are saying that moments to the right hand side constitute the clockwise moments, or moments that cause the bar to move in a direction that is clockwise or similar to that direction of a clock. Then those are what we call the clockwise moments. So we are saying that in this case actually the moments to the right hand side constitute the clockwise moments, whereas the moments to the left hand side constitute the anti-clockwise moments. So like in this diagram of mine here, actually F1, the force F1 and the force F2 will produce what we call a clockwise moment. Why? Because suppose force F2 represents a weight which is actually acting downwards. If you place a weight on this particular object, on this particular bar, that weight will cause this bar to move in this direction. That is because you are placing a weight here and the weight acts downwards. It will pull this object, it will pull this bar to rotate in this direction. That is about our pivot here. So if it is moving in this downward direction, so remember the downward direction is the same as the direction in which the minute hand clock or the hour clock of a normal wall clock will actually move. So because it is moving in a direction similar to that of a clock, then we say that force F1 and F2 will produce what we call a clockwise moment. Why? Because they will cause the bar to move in a direction similar to that of a clock. That is the hands of a clock. So F1 and F2 represents the clockwise moment. So that's why we are saying that the clockwise moments will be represented by the force that is F1 and D1, then F2 and D2. So we are saying that F1 and F2 will produce clockwise moments because they cause the bar to move. Their effect causes the bar to move in a direction similar to that of the clock, or they cause the bar to move in the clockwise direction. Conversely, force F2 and force F3 and F4, they will cause the bar to move in this direction, which is of course opposing the clockwise direction. So to oppose means to anti, that is anti-clockwise. So remember, if something is producing an effect opposite or controversial to that of the desired effect, then we call that an anti. For example, you've heard of antivirus because they fight the virus, or they produce an effect which is opposite to a virus. If you've done biology, you have also talked of antibodies. So antibodies will always fight the antigens. They always fight the antigens. So anti means it is the opposite of the clockwise. So if you are talking of anti-clockwise direction, it means it is moving in a direction that is opposite to the direction of the minute hand or the hour hand of a clock. So anti-clockwise direction represents this direction. This is the anti-clockwise direction. Whereas this direction, this is the clockwise direction. So because these forces F4 and F3 will actually, their weight will cause the bar to move downwards. So downwards about this particular pivot, downwards it means the bar will move in this direction, which is the anti-clockwise direction. That's why you are saying that force F4 and F3 will represent the anti-clockwise moment. So I think we've discussed enough on how to identify those forces. So it is just important to note that the forces that causes the bar to move in the clockwise direction will produce the clockwise moments. In this case, force F1 and F2 will cause the bar to move in this direction, the downward direction, which is the clockwise direction. Hence they represent the clockwise moments. Whereas force F3 and F4 will cause the bar to move downwards or in the in this direction, which is actually opposing the clockwise direction. So we call it the anti-clockwise direction. That's why we are categorizing F3 and F4 under the anti-clockwise moments. Remember, if you had F1 but being directed upwards, it means it will cause the bar to move upwards in this direction. So remember, this direction will be the anti-clockwise direction. So in that case, F1 would represent the anti-clockwise moments. So the most important thing is to look at the effect of the force on the bar. In fact, the direction or the position where the force is lying does not have the effect. So the effect, you just look at the effect of that force on the bar. If it is causing the bar to move downwards or in this direction, then it will constitute the clockwise moments. Then if it is causing the bar to move upwards or in this direction, then that would represent the anti-clockwise moments. Why? Because they will cause the bar to move in the anti-clockwise direction. So in this case, we are saying that, remember the principle of moment stated that for a system in equilibrium, the sum of clockwise moments about a point must be equal to the sum of anti-clockwise moments about the same point. So the word sum in mathematics means addition. So if we have two or more moments having the same effect, then we add them. So the sum of clockwise moments. So like in this case, F1, so remember moment we defined it as the product of force and the perpendicular distance. So force F1, its perpendicular distance from the pivot is actually this distance, that is D1. Then force F2, its perpendicular distance from the pivot is actually this D2. So remember that all the forces have to be measured from the pivot and they must be perpendicular. That is, they meet perpendicular with the line of action of the force. So we are saying that the force, the moment due to F1 will be F1 times the distance D1. That is its distance from the pivot. So F1 D1. So because it is causing the bar to move in this direction or the clockwise direction, therefore it is a clockwise moment. Then the sum, we are adding another force which is having similar effect, that is causing the bar to also move in the clockwise direction. So force F2, its moment will be F2 times D2. That is its perpendicular distance from the pivot. So F2 times D2 will also represent the clockwise moment. So because there are two forces, therefore we sum them or we add them. So sum in mathematics means addition. So remember, we did say that the physics and mathematics have a very close relationship because physics concepts are always expressed mathematically. So if you add those one, or when you sum the clockwise moment, then this represents the clockwise moment. Then the forces that are causing the bar to move in the anti-clockwise direction, that is in this direction, F4 will cause the bar to move in this anti-clockwise direction. That is a direction opposite to that of the clock. Then F2 will have a similar effect. It will cause the bar to move in this direction, that is in the anti-clockwise direction. So the moment due to F4 and F3 represent the anti-clockwise moments. So F4, the force F4 times its perpendicular distance from the pivot represents the its moment. Then the force F3 times its perpendicular distance from the pivot represents its moment. So F3 D3 plus F4 D4 represents the anti-clockwise moment. So the sum, because we are adding those two. Then we look at an example involving those calculations. So example 1 here reads that a uniform meter rule pivoted at its center. Remember, when we are talking of a meter rule, it means it is a ruler which is 1 meter. So 1 meter is equals to 100 centimeters. So a uniform meter rule pivoted at its center is balanced. Remember, the center of a meter rule will be the 50 centimeter mark, because a meter rule is 1 meter, which is equivalent to 100 centimeters, and 100 centimeters divided by 2, you get to the 50 centimeter mark. So a uniform meter rule pivoted at its center is balanced by a force of 4.8 Newton at the 20 centimeter mark, and some other two forces, F and 2 Newton, on the 66 centimeter mark and the 90 centimeter mark respectively. So we are required to calculate the value of force F. We are required to calculate the value of force F. So remember, actually here the first thing is to sketch, so that you see how the forces are actually aligning themselves. So first of all, we are told we have a meter ruler. So a meter rule runs from the 0 centimeter mark up to the 100 centimeter mark. Then it is pivoted at its center. So that means the pivot is at the center. So the center of 100 centimeter mark is actually the 50 centimeter mark, or the 0.5 meter mark, because the whole thing is actually 1 meter. So it is pivoted, meaning the pivot is actually at the 50 centimeter mark. So you can see my pivot is actually at the 50 centimeter mark. Then it is balanced by a force of 4.8 Newton at the 20 centimeter mark. So if this is my 0 centimeter mark, then the 20 centimeter mark will be around here. So at the 20 centimeter mark, we have a force of 4.8 Newton actually acting from there. Then, and some two forces, that is F and 2 Newton, on the 66 centimeter mark and 90 centimeter mark respectively. Respectively means in that order. So it means our force F is acting at the 66 centimeter mark. So you can see here my 66 centimeter mark, we have a force F. Then 2 Newton is acting at the 90 centimeter mark. So I have my 90 centimeter mark, I have a force of 2 Newton actually acting from there. Then I also have, we are required to calculate the value of force F. So from the principle of moments, actually the sum of clockwise moments must be equal to the sum of anti-clockwise moments. So whether you choose to start with anti-clockwise or clockwise, it is one and the same thing, as long as you have the sum of clockwise moments being equal to the sum of anti-clockwise moment. Then we did say that anti-clockwise moment constitute the forces that will cause the bar to move in a direction which is opposite to that of the minute and the hour clock of a watch, which is the anti-clockwise direction. So if you look at this force, that is force 4.8 Newton. So because it is acting downwards, it will actually cause this bar to move in this direction. So actually this direction from the bar, this direction is actually a direction which is opposite to that of the minute and hour clock of a watch. So actually, because it is causing the bar to move downwards or in this anti-clockwise direction, so force 4.8 Newton will constitute our anti-clockwise moments. So you take the force F1 times its perpendicular distance from the pivot. So if the pivot is at the 50 centimeter mark, then the force 4.8 Newton is at the 20 centimeter mark. Then the perpendicular distance from the pivot will be 50 centimeter minus 20 centimeters, which is actually the 30 centimeters. So I have F1 times D1, which is the 4.8 Newton, times the 50 minus 20, which is the perpendicular distance from the pivot. So you actually get 30. But because it is in centimeter, and we did say that the SI unit for length is actually meter, so that means we convert it from the centimeter to meters. So we know that 100 centimeters is equals to 1 meter. So what about 50 minus 20, or the 30 centimeters? So it will be 30 divided by 100. So I have 4.8 divided by 30 divided by 100, which is actually in meters. Then after that, I have I look at the sum of the clockwise moments now. So we said that clockwise moments will always cause the bar to move in the clockwise direction. So this force about this pivot, it will cause this bar to move in this direction, which is the clockwise direction. It will also cause the 2 Newton will also cause the bar to move in the downward direction, which is actually the clockwise direction, because it is a direction similar to that of the minute hand and the hour hand clock of a watch. So it means we have 2 clockwise moments. That is the one produced by force F and the one produced by a force of 2 Newton. So here we are talking of moments because there are 2, but here it is only 1. That's why I'm talking of just a moment. So we have two forces which are the clockwise moments. So I have the force due to the F, that is the force F, which is placed at the 66 centimeter mark. So I have its moment will be F times its perpendicular distance from the pivot. So the perpendicular distance of F from the pivot will be 66 minus 50, because the pivot is actually at the 50 centimeter mark. So 66 minus 50. So I have F times the 66 minus 50, which actually comes to, I think that will be around F times around 16. So the difference will actually be 16. So 66 minus 50, I get 16, but divide by 100, that is to convert it into meters, because those are the SI unit for length. Then plus, I'm adding, that's why you are talking of summation. Then plus F3 D3, F3 because it is also an clockwise moment, because it is causing the bar to move in the clockwise direction. So I have F, then its perpendicular distance from the pivot will actually be the 90 from the pivot. That is 90 minus 50. So I have 2, which is its force, times its perpendicular distance from the pivot, that is 90 minus 50. So 90 minus 50, but to convert it into meters, I divide by 100. So I have 90 minus 50. So if you subtract those two, you actually get 0.3. That is 30 divided by 100, you get 0.3. So that I have 4.8 times 0.3 being equal to, here I have 16 divided by 100, which comes to 0.6. So I have F times 0.16. Then plus, here I have 90, 50 minus 90, you actually get 40, divided by 100, you get 0.4. So we have 2 times 0.4. So if you multiply 4.8 times 0.3, you get 1.44. Then if you multiply F times 0.16, you simply get F times 0.16. Then if you multiply 2 times 0.4, you get actually 0.8. If I do collect the like terms, I'm taking the 0.8 to this other side, so that I have 1.44 minus 0.8. Then here I've remained with F times 0.16. So actually 1.44 times 0.8, you get 0.64, which is equals to this other side. I'm still having F times 0.16, which is actually F times 0.16. So if I divide both sides by 0.16, I'll have F being equal to 0.64 divided by 0.16. So if I divide, you actually get 4 Newton. So you get 4 Newton. We look at another example which involves with the same. So the example reads that a uniform meter rule is suspended vertically from a pivot at the 0 centimeter mark, full stop. It is maintained in vertical position by 3 horizontal forces acting in the direction shown below. Then given that the 12 Newton force acts through the 10 centimeter mark, while the 8 Newton force acts through the 90 centimeter mark, calculate the force F which acts through the 60 centimeter mark. So as usual, the calculation is the same. So we say sum of clockwise moments will always be equal to sum of anti-clockwise moments. So we said that clockwise moments will always cause the bar to move in the clockwise direction. So if you look at this diagram, this will only be the clockwise moment, because it is causing the bar to move actually in this direction. So if I have the pivot here, this force will cause the bar to move in this direction. So this direction actually is what we are calling the clockwise direction. So this will represent the clockwise moment. So I have clockwise moment here being equal to the force times the perpendicular distance from the pivot, so that I have my force F here. Then its perpendicular distance from the pivot, because it is at the 60 centimeter mark, will be 0 minus 60. So if you take 0 minus 60, you simply get 60. So we have a force F times 60, but to convert it into meters, I divide by 100, so that I have F times 60 divided by 100. Then this will be equal to the sum of anti-clockwise moments will be F times D. So I have 2 anti-clockwise moments here, that is the 12 Newton and the 8 Newton. So because they will cause the bar to move in this particular direction, so if I apply a force 12 Newton moving in this direction, it will cause this bar to move upwards. So the upward, this one is representing the anti-clockwise moment. So the force of 12 Newton and 8 Newton will represent the anti-clockwise moments. So the sum of anticlockwise moments, I will add all the forces which are the anticlockwise moments. So I have the 12 Newton force and the 8 Newton force. So that I have the sum of anticlockwise moment being represented by the 12 Newton force and the 8 Newton force. So here, the clockwise moments, I only have the F. Then the anticlockwise moments, I have the 12 and the 8, because these two forces will have an effect of the bar moving upwards or in the anti-clockwise direction. So here I have the force here, I have 60 divided by 100 because its distance from the pivot is 60. Then for this case, the 12 Newton force, its distance from the pivot is actually the 10 because it is at the 10 centimeter mark. So I have 10 minus 0, you actually get 10. So here I have 12 Newton times 10. Then to convert it into meters, I have 10 divided by 100 because 100 centimeters is equals to 1 meter. Then I add another 8 Newton force because it is also acting in the clockwise, anti-clockwise direction. So it is acting from the 90 centimeter mark. So its perpendicular distance from the pivot will be 0 because the pivot is at the 0 centimeter mark. So it will be 90 minus 0, which comes to 90. So its moment will be the force, that is 8 Newton times perpendicular distance from the pivot, which is 90. So I have 8 times 90. Then to convert the 90 into meters, I simply divide by 100 because 100 centimeters is equals to 1 meter. So I have 8 times 90 divided by 100. So if you compute this one, 60 divided by 100, you get 0.6. So we have F times 0.6 being equal to 12 times 10 divided by 100, you actually get 1.2 Newton. Then 8 times 90 divided by 100, you get 7.2 Newton. So if I add the like terms, I have 1.2 plus 7.2, you get 8.4 Newton. Then F times 0.6. So I have F times 0.6 being equal to 8.4 Newton. So if I make F the subject of the formula, I'll divide both sides by 0.6 so that I remain with the F on the other side. So I have F being equal to 8.4 divided by 0.6. So you divide 8.4 divided by 0.6, you actually get 14 Newton. You get 14 Newton. Our third example reads that the figure below shows a system at equilibrium under several forces. So you are required to determine the value of the force P. So here the formula is the same. You just say the sum of clockwise moments must be equal to the sum of anti-clockwise moments. So we did say that clockwise moments will have an effect on the bar such that the bar moves in the clockwise direction. So if you look at the 4 Newton force, this one will cause the bar to move in this direction. So this will be the anti-clockwise direction. You look at the 8 Newton force, it will cause the bar to move downwards. So this is the clockwise direction. So considering this is the turning point of the pivot, 8 Newton force will have and will cause the bar to move downwards or in the clockwise direction. So the 8 Newton force is the only force that is representing the clockwise moments. Remember, our force P is causing the bar to move upwards. So relative to this turning point, force P will cause the bar to move upward. So upward direction, that is representing a direction which is opposite to that of the clock. So that is the represent the anti-clockwise moments. So we only have the one clockwise moment, that is the 8 Newton force. So we have FD. So FD will be the force 8 Newton times its perpendicular distance from the pivot. So my 8 Newton force is at a distance of 40 centimeters from the pivot. So its moment will be 8 Newton times the perpendicular distance from the pivot. So 8 Newton times 40 centimeters. So I have 8 times 40 centimeters. So to convert the 40 centimeter into meters, I divide by 100 because we all know that 100 centimeters is equals to 1 meter. Then sum of anti-clockwise moments will be the P, the force P, because it is causing the bar to move upwards. So the upward direction actually is this direction, which is actually the anti-clockwise direction. Then this force is causing the bar to move downwards. So remember, downwards is this direction. So this is also the anti-clockwise moments. So the force of 4 Newton and the force P, they are both anti-clockwise direction moments because they are causing the bar to move upwards or in the anti-clockwise direction. That is relative to our pivot here. So here we have FP times DP, which is representing the anti-clockwise moment. Then you also have a force of 4 Newton and its perpendicular distance. So we have force P times 50, because that is the distance of P from the pivot. So we have 40 plus 10. So from the pivot to P is actually 50 centimeter. That's why we are taking 50. Then to convert it into meter, we divide by 100. Then plus another force here, 4, which is actually 35 centimeters from the pivot. That is our force of 4 Newton from the pivot is actually 35 centimeter. So to convert into meters, which are the SI unit, we divide by 100. Then you solve this one, 40 divided by 100, you get 0.4, which is times 8. Then P times 0.5, that is 50 divided by 100, you get 0.5. Then plus 4 times 35 over 100, you get 0.35. So you multiply 8 times 0.4, you get 3.2. Then you multiply P times 0.5, you get 0.5 P. Then if you multiply 4 times 0.35, you get 1.4. So from here I collect the like terms. I take the 1.4 to the other side, so that I have 3.2 minus 1.4. Then this side I've remained with 0.5 P. So 3.2 minus 1.4, you actually get 1.8. Then 0.5, I divide both sides by 0.5 to remain with P alone, so that P will be equal to 1.8 divided by 0.5. So you take 1.8 divided by 0.5, you'll actually get 3.6 Newton. So you get 3.6 Newton. So that will represent our force P. So the most important thing is to note that which force represents the clockwise moments and which force represents the anti-clockwise moments. And what will help you to determine which force is the clockwise and anti-clockwise, we said you just look at the effect of that force on the bar. Like this one here, it is moving upwards, so it will cause the bar to move upward. So if you look at relative to the pivot, the upward direction, it will represent the it will cause the bar to move in the anti-clockwise direction. Hence P represents the anti-clockwise moments. Then 4, it will cause the bar to move downwards. So this direction is also the anti-clockwise direction. But the 8 Newton, it will cause the bar to move in this direction, which is the clockwise moments. That's why we are saying that the 8 Newton force is the only clockwise moment here. Then the 4 and the force P will represent the anti-clockwise moments, because they causes the bar to move in the anti-clockwise direction that is relative to the pivot or our turning point. And lastly, I have some exercise which will help you see whether you understood our examples. So the first exercise reads that a uniform meter rule is balanced at 80 Newton and 20 Newton from its end. Find the position of the pivot from the 20 Newton end. So the expected under is 80 centimeter or 0.8 meter. So try and see whether you get the same. Question 2 reads, the figure below shows a bar AB of negligible weight. Remember, negligible weight means we are assuming the bar has no weight, or the weight of the bar is actually 0, so it will not be considered into calculations. Weight which is pivoted at A, so the pivot is actually at A, full stop. Find the value of R if the bar is in equilibrium. So just to give you a hint is that if R is acting in this manner, its effect on the bar, remember when you pull the R downward, this a pulley, it is movable. Actually, when R is pulled downwards, actually this rope here, it will be pushed upwards. So the effect of the force R on the bar is actually upward. So it causes the bar to move in this direction, the upward direction, which is, of course, if the pivot is here, it will cause the bar to move in the anti-clockwise direction. So in this case, the anti-clockwise forces will actually be force R. It will be an anti-clockwise moment. Then question 3 reads, the figure below shows a uniform bar of length 50 centimeters and negligible weight. So you are required to determine the distance marked X and Y if the bar is in equilibrium. So the expected answer is that Y will be equal to 18.75 centimeters, then X will be equal to 13.25 centimeters. So this is our diagram here. So try working out and see whether you get the same. In case you have problems in solving it, just drop a comment on my channel, then I'm there to respond. So we've come to the end of our class today, but we need to discuss the quote of the day. So the quote of the day said that if you don't take time to heal from the pain of your past, then be prepared to bleed all over your future. So what does this particular quote mean? So the quote means that after we've gone through a painful moment in our lives, usually everyone wants to move on quickly, as if nothing happened. As much as it is good to move on, but you must remember that you must remember one fact, and the fact is that if you don't allow yourself time to heal from the pain, that was caused by the difficult moment that you went through in the past, then you will be carrying the pain from your past to your future life. So allow yourself to be to feel and experience those painful emotions before deciding to move on to your future. I know that it will take time to heal from those emotions, but once you are fully healed from them, you will always be at peace with yourself. But if you decide to suppress those painful emotions without acting on them, then expect depression in future. So accept the fact that everything in life happens for a reason and for a season. Forgive and show kindness even if you are the one who was wronged. And more importantly, have the courage to move on. And lastly, if you don't take time to make peace with your past, then your past will always ruin your peace in future. So this is Kind Tuition Academy. Kindly hit that subscription button on YouTube. Thank you.